Sound good?
Sounds good.
Yep.
Okay.
Oh yeah. Well, I will treat you as a moderator, and
Yeah.
Matthew as a colleague / competitor.
All right. We're here for this week's podcast, which is in video form via the magic of the internet. I brought on some colleagues and friends this week to help, and my idea is to give both of them a challenge, but all of you an insight into what would two experts do if I gave them this assignment. And they've already been bugging me about, they both kind of know exactly what they would do. So to give a quick introduction, I'll start with Dr. Matthew Cross, who is a PhD from the Department of Engineering at Western Electrical
Electrical and computer.
Electrical and Computer. He is the head at Western of the Canadian CubeSat project, or the lead engineer.
I am the project manager for Western's CubeSat project.
That's yeah, the head.
The head, yeah.
The head engineer. He's also worked at the European Space Agency, been on multiple projects with the Canadian Space Agency for analog rovers and mission design, which is exactly what we're talking about today. And is currently in Nanaimo. So it's dark where I am, but because of the Earth's curvature, that light not reaching me, but definitely hitting Matt. And so below him is Dr. Raymond Francis, also a PhD from the Department of Computer Engineering.
From the same Department of Electrical and Computer Engineering.
Yeah, there we go. Raymond has much a similar background. He's got a lot of his start on planetary science stuff, Canadian Space Agency analog missions at Western, but is now in Pasadena, California, working on the Mars 2020 rover and also Mars Curiosity. So I'll give both of you an opportunity to fill in any blanks. Matt, anything I miss or any introduction that you prefer?
Yeah, Matt Cross. I'm currently, as Danny mentioned, in Nanaimo, but otherwise I am a postdoc at Western. And in that role, I'm managing the CubeSat project. And there are some other space projects that have come out of the Western Space Institute that I'm actively a part of. And also a remote research affiliate with the Jet Propulsion Lab. So I've gone down to visit Raymond on a couple of occasions. And yes, thanks to the curvature of the Earth, it is still somewhat sunny here, but that is being darkened a little bit by some smoke from flaming forests in the US. But yeah, otherwise engineering, I do things.
Dr. Francis, yourself, I think I introduced you decently.
Yeah, sure. I mean, I work here at the Jet Propulsion Lab, which is NASA's sort of premier facility for planetary science missions, robotic missions to explore the solar system, but we also do astronomy and heliophysics kind of missions and Earth missions, which I think are often forgotten. And my specialty here is a mix of planetary mission operations, usually with the rovers on Mars, and but also research in onboard autonomy, in getting robots to make decisions for themselves about how to do science on missions. So some days I operate rovers and some days I teach computers to operate rovers.
Are you teaching yourself out of a job?
No, and in fact, that's something we really try to tell the scientists is we don't want to replace the science team on these missions. We want to give them smarter tools.
It's a good line. Okay, well, so I was thinking about this, and I mean, this assignment, the final assignment is built off of two other ones. And this is the first part, which is to really pick their planetary body and their region or feature of interest. And in hindsight, this is probably where I should have had some geologist friends on, and then had the two of you on the next part, which is much more like choosing instruments and things like that. But we'll do it backwards, and we can still talk about instruments at the end anyhow, or designs. But yeah, obviously, you know, in a nutshell, the final project is design a dream mission, a planetary science mission. And this is something you guys have thought about a lot. And you start with picking a planetary body and something about it you want to learn more of. So with that in mind, Raymond, where would you start?
Okay, so the solar system is a big place. There are lots of interesting places to go. And I think we probably all have our own aesthetic ideas of what is the most interesting place. But the planetary science community has been thinking about that in a very organized way for a long time. And they now have a process where they get together every 10 years to decide what they'll do for the next 10 years. And so they've laid out their priorities in a publicly available document called the Planetary Science Decadal Survey. And never mind picking a planet, I think that's the best place to start with deciding where to go.
Dr. Cross, do you concur?
I concur. And if you take a look at that planetary decadal survey, and like you can look at the surveys from past decades just to see how those objectives have evolved over time. But looking at the most recent decadal survey, they look at the solar system and identify what is the science community's most pressing interests. And they actually list out in the document what are the questions that we still want to know. What are we trying to find out? And it's organized by different groups. So like the outer gas giants, or the inner rocky bodies. And the questions that have been formed also cross different different regions, and there's general questions, or there's more specific questions. So looking for the right question to ask, I would go to the decadal survey. But sort of thinking about that a little more, there's also like who is actually putting this together, because the decadal survey is the representation of the planetary science community, and those were their top priorities. But there may be some that were left out, and so the various groups that have contributed to the decadal survey, they themselves will have a list of priorities, and maybe only the top number will get listed in the decadal survey. So for example, there's the Lunar Exploration Analysis Group will have their own, like that, and that's a working group on lunar science. And so they themselves will have their own published reports on the types of science questions that they still want to ask. And there's even proposals and stated proposals as to how they might start to answer them. There's also the Mars, or MEPAG, Mars something.
It's the analysis. Mars Exploration Program Analysis Group.
That's the one, yeah, MEPAG. And so there are these working groups that produce these reports, and which act as like guideposts, and in terms of what to do next, what are the unanswered questions, and those groups start to provide suggestions as to how those questions might be asked. And so I was able to go online today and download a free copy of the decadal survey, and there are loads of references properly cited in the document, and so that would be a great resource to begin.
Yeah, these documents, and I'm glad that Dr. Cross mentions the analysis groups, because that is a great background. I think the decadal survey is a great place to start. Might be the place to pick where or what kind of place you might want to go. Maybe you think maybe the decadal survey leads you to believe that outer planets are the destination, and then go to the outer planets analysis group and see what they really want in detail. That might be if you really wanted to track how this is done, because these are reports that are produced by the community of planetary scientists with consciousness of budgets and available technologies, and they're meant as a guide to the space agencies of, this is what we should do, this is where you should put your resources. And they're also kind of a guide to people who do for real what will be asked in this assignment, people who pitch missions, people who propose planetary exploration missions of one scale or another.
Yeah, it's one of those, like what we call in policy work, like a grounding document, or we sometimes call it policy cover, where it's like, if you can find a definitive group that has stated your objectives to be critical, you keep harking back to it. You say, look, these people say we need this. It's similar like when the government has a speech from the throne. If that speech from the throne mentions your thing, every single time you write about it, you mention, our prime minister mentioned this in the speech from the throne. Same with when you pitch a mission. If it tags back to something that's a high priority in the decadal survey, that's your go-to kind of pitch. Now, at the same time, I don't want to dissuade students from going off the board a little bit, but Raymond, you have a point?
Well, I think, yeah, I mean, it might seem boring that we're this many minutes into a discussion of where to go in the solar system, and we haven't discussed anything in the solar system yet. We're still talking paperwork. But this is, you get to do the exciting part of dreaming up space missions because you have a reason to go there. And the Planetary Decadal Survey and the analysis groups, these are the things that lay out the reasons to go there. These are the justifications for your starry-eyed dreaming. So, yeah. And as you say, I think not only you should not confine yourself to the priorities of the decadal survey. If you look at missions that got proposed in recent rounds of proposal, they're not always the high priority missions from the decadal survey, because sometimes the top priority thing, the decadal survey that we're talking about, the most recent one from 2012, laid out 3 top missions. These are the things that we most want to do. But sometimes the big one has already been put into development, and sometimes there are 15 other cool things that are not the top 3, and maybe you have a way to do one of those on a low budget that fits. So there are lots of things to do, but I think it's worth looking at this guidance.
And as this is a class assignment, you could even take a different approach. Like, you might think, hey, Neptune's kind of cool. What questions are still to be asked about Neptune? And there's the survey report will tell you, here's the open questions about Neptune, and then there will be a working group who have fleshed out even more information and details on that. So, from a class assignment perspective, if there's something cool, you can use that as a starting point and your search term for looking through the document.
For sure. And I would say, if we're about to start moving into talking about real destinations, I think actually Neptune is a compelling destination for reasons maybe we can get into.
Yeah, we will. And I think Matt brings up a good point. Like, it's a class assignment, so you can definitely have some leeway. And, the reality of the decadal survey, I want everyone to stay within the realms of what Raymond mentioned, realistic technology, and things like that. I mean, there's not, landers for the core of Saturn or anything crazy like that. But there are, Matt's thinking, but, something like Neptune, for a variety of even social and cultural reasons, might be pretty low on the decadal survey. But from a pure scientific perspective, there might be a lot of really interesting things about it. And then there's also things like how far away are things and how long until we actually get mission data return. And sometimes that plays into, do you really want to fund a mission that's not going to have anything, it's going to be sleeping for 10 years and there'll be 2 different presidents by now.
Well, and that's also, there's another thing that we haven't mentioned yet here, which is sadly one of the big drivers, which is the budget. You know, there are things you can do with a $2 billion, what we call the flagship mission. And there are things you can do with the like $1.5 billion middle tier mission. And there are things you can do with a few $100 million. But if, you know, if you've got $50 in your pocket, you're not going to space today. So it, the budget will determine in detail what it is you can achieve. And I don't know how much you want students to consider that, because it's a challenging thing to learn to pull in. But the budget envelope does explain why sometimes the highest priority thing has not yet been done.
Yeah, I think we're going to talk about it throughout the course. I haven't laid out the specific details for the final project just yet. But like you say, I mean, everything tends to fall within the $500 million to, barring it's a long-term program like Apollo or something, 2 billion. So we'll talk about that throughout the year. But right now I want the students thinking about the science, and we'll think about the cash later, which is the opposite of unfortunately, reality.
Yeah, but I think that's fair. It's worth noting that the highest priority thing that was identified, spoiler for the 2012 decadal survey, was Mars sample return, on condition that it was affordable. That was literally the thing they said. Mars sample return, if you can afford it, here's how we think you could afford it. And as it turns out, that's more or less a thing that's being implemented. So.
Awesome. Okay, let's kind of see what you two stay up worrying about that we don't know about the solar system. And I mean, I'm sure, Raymond, you worry about Mars a lot, and Matt probably the moon, because your various projects tied to these things. But I'm actually kind of curious. I don't think I've ever talked to either of you about things other than those two bodies that much. And feel free to talk about the moon or Mars if you want. But let's go to Matt. A couple of mysteries, maybe one big one, and maybe a couple other you're interested in.
So there's, you know, thinking about this, there's a couple of different options. You know, one of the big questions, of course, is there evidence of life somewhere in the solar system, and life that may have formed and evolved on another planetary body? And so, of course, there's, you know, active missions and proposed missions for you know, the study on Mars. And you know, we have a recent announcement for you know, from the potential that life may exist in the Venusian atmosphere. But there's some other interesting places in the solar system where the science suggests that the conditions for life may exist, and those are out in the outer solar system, in the various ocean worlds, and or bodies that may have some kind of aquatic activity that could support life. And so one moon that has interested me is Enceladus. And so moon of Saturn, you know, existing mission, Cassini, captured what appear to be geysers, you know, shooting what appears to be some kind of liquid from the subsurface. And so it's been proposed that if there is some kind of liquid subsurface, which would, you know, generated which would be liquid from heat generated from like tidal forces from Saturn, you know, maybe that's a possibility for a source of life. And so the question is, you know, I look at it from a technical perspective. It's an interesting science question, but I look at it from a technical perspective of, like, if there is subsurface, like if there is a subsurface condition for life, and, you know, if that is possibly present, how could we determine if life exists on Enceladus? And so there's been some ideas of like trying to fly through the plumes and capturing and analyzing that plume material for signatures. There's been some more exotic proposals of trying to actually like fly into the plume using some kind of kind of like a penetrator that would just fly into the source of the plume and actually get into the subsurface. These are all interesting technical challenges, but ultimately it's a question for is there evidence to suggest that life may exist on Enceladus? And so that's kind of like a fun big idea. You're looking going to the moon, which is sort of more in my current wheelhouse. So some of the even though there's been missions to the moon, there's been crewed missions to the surface. We have samples returned from the surface, but there's still so many questions that remain unanswered. And there's so many questions about the solar system, the formation of the solar system, even the formation of Earth. And these are the kinds of questions that can be answered by further investigations on the lunar surface. Like, sure, there's been some astronauts have gone to the surface, and we've had some rocks return, but that represents a very small fraction of the surface. And so while we have an idea of what what the regolith is and what it contains from this drill core, we don't know how well that generalizes across the entire moon. And so, and there's also questions as to like how old is the moon, or what are what were past like cryovolcanic processes. Like there's evidence to suggest that there have been cryovolcanism processes on the moon, but how do we constrain that, and how does determining when those events took place, how does that fit into the overall picture of solar system formation? And so there's a lot more opportunities to with upcoming commercial missions to the surface. That we have evidence from various orbiters, like the Lunar Reconnaissance Orbiter, with various multispectral images and being able to characterize the surface. And then now there's proposals for landers or for rovers, both commercial and also agency led. There's a lot of opportunity to start studying more of the surface and answering some of those questions. So the moon is interesting, and it's there, and there's a lot of upcoming opportunities for studying it, and still a lot of questions to be answered.
Okay, before I jump to Raymond, you brought up a couple things I want to, well, we'll touch on them a little bit more, but Matt mentioned solar system formation, which is what this week we were talking about as kind of the grand mystery at the bottom of it all, along with whether or not there's life elsewhere in the solar system. But definitely something to keep in mind when thinking about mysteries. And I'll come back to you, Matt, so maybe you want to start thinking, now that you've named your mysteries, I might follow up with what kind of things might you throw at those mysteries. So whilst Raymond goes over his, have that in mind. So Raymond, like you said, Mars mysteries very well, but either along with Mars or other than Mars, what would you look at?
Yeah, so Matt hit on two of the big questions, right? Is there life? What are the conditions for life? And we often answer that question in a very narrow sense of like what puddle could bacteria live in or something. But the second is answering it in the big sense of how did the solar system form? Because we know the solar system is habitable. The Earth is in the solar system. So what was the environment around the Earth when life was forming? And what did the other planets look like at that time? and that includes the Earth's moon. Had Matthew not mentioned it, my first story would have been about how important sample return from, let's say, the oldest of the lunar basins might be. So that's, I think, a very, the Earth's moon is right there, and there's a lot yet to do. But okay, keeping in mind where is good for life, what is life, how does it fit, and how does the solar system form? Let's move on to some other places. So one place that doesn't get a lot of attention for those two questions is Venus, although this week there's been some buzz. But, Venus, as a reminder, is a planet that's very similar in size to the Earth, very similar in surface gravity to the Earth. It's a little closer to the sun, but it looks completely different. It is covered in thick acidic clouds. It has a surface temperature of hundreds of degrees Celsius that melts almost anything. It seems like it's not a good candidate for life. But the indications are that Earth and Venus and Mars, which are all in like the habitable region of the sun, if we were looking at this solar system as an exoplanet solar system, we would see 3 planets in the habitable zone, 3 planets where, atmosphere aside, you could probably have liquid, solid, and gaseous water coexisting. So why does Venus, with the same surface gravity and forming out of the same original nebula, look so different to Earth, which is right next to door in that solar nebula, and yet somehow, and about the same size, but somehow looks very much more clement here on Earth? It seems like Venus looked like the Earth at the start. This is one of the leading hypotheses that 3 or 4 billion years ago, Earth, Mars, and Venus had very similar surface conditions, lots of water laying around, and clement temperatures. And now Mars is cold and has little atmosphere, full of carbon dioxide. Venus is hot and has too much atmosphere, full of carbon dioxide. And so Venus went through, both of those planets, but Venus in particular here went through some runaway change in its climate. It got a lot hotter. There's a lot more CO2 in its atmosphere. It is an extreme example of climate change. That's the current hypothesis on a terrestrial planet. Wouldn't it be nice to know what happens when terrestrial planets go through radical changes in their atmospheres? And wouldn't it be nice, we make all kinds of generalizations about life based on Earth. We have one example. And we have one example of an Earth-sized planet with an active atmosphere and active geology. Only one that we've ever gone to. We've had a couple of very short surface missions to Venus. But other than that, aside from some orbiters with some radar, we have like really limited understanding of how that planet got to be, and it's our closest neighbor. I made this analogy. What if we were looking at our solar system from a distance as an exoplanetary system? We might mistake Venus for Earth. There would be a newspaper headline that says Earth-sized planet found in habitable zone, but Venus is not habitable by any of our expectations. So here we have a model for an exoplanet that doesn't behave the way we expect. Maybe we should go look at it, because the exoplanets are hard to get to. So I think Venus ties into a lot of these questions. Another thing that we touched on a little earlier, I said Neptune was an interesting place. We've sent long duration missions to all of the inner planets that have lasted months and years, and to Jupiter and Saturn, years on orbit at those destinations. But the outer planets, the further outer planets of Neptune and Uranus, each of them has one brief flyby by one spacecraft with, launched in the 70s with a 1960s computer. Yeah, that one. And so aside from Voyager, that one flyby each of Voyager, we really don't have much information on those planets or their satellites. And nowadays, I think 30 years ago, they might have been lumped in as gas giants with Saturn and Jupiter, but nowadays they're described as ice giants because they're so much colder. And so what is a cold, gaseous atmosphere behave like? How does it form? Why is it different? Why do they seem similar but also different? And certainly different from the inner, larger gas planets. And while you're there, take a look at the satellites. Some of the satellites of those planets look like captured copies of Pluto. They seem like large Kuiper belt objects with their own very strange geology and active surfaces that may be, preserved remnants of the cold outer part of the solar nebula. So an orbiter mission, even, without choosing a mission design, but a long-lived or at least high data quality mission to one of those planets would tell us a lot about the formation of the solar system and its history since. And then I guess my third theme is, I'll say, speaking of those little bodies that got captured by the ice giants, there are little bodies all over the solar system, and we have wildly undersampled them. There is more diversity in asteroids and comets and Kuiper belt objects than we even know at this point. So, and those are missions that are often achievable on small budgets, even with long timescales. Little spacecraft can go and meet a comet and learn a lot about it. So, yeah, these are some of the themes that I have in mind.
I like that. And maybe it's because I'm in the space bubble, but I definitely feel like Neptune and Uranus are getting more attention, but maybe that's just the people I follow online. Yeah, you pointed out, Triton is a moon of Neptune that just, there's conspiracy theories and all sorts of things about our solar system, about secret planets and things that are, we don't need those. There's weird enough stuff as it is, Triton being one of them. It's in a retrograde orbit around Neptune, which means it's going backwards for some reason against the entire force of the solar system. So, it might have cryovolcanism, which is a fancy way of saying ice volcanoes. So Raymond, you hit on something really, really interesting there that I don't know how much that's represented in the decadal survey.
I think the ice giants were like a third priority, and so they didn't get reached in, the top two priorities, Mars sample return and icy moons. They picked Europa for that. Matthew mentioned Enceladus, but there are other candidates, and so those two are like under construction now. But the ice giant mission is still waiting on the table. Of course, a little research will reveal that it takes a long time to get to Neptune or Uranus after you launch the thing, and you'll probably spend a decade developing it.
Well, that's the other pain in the ass about our solar system, is how big it is. And that's our close neighborhood in many ways. Even Uranus and Neptune are still our close little neighborhood when we start talking about things like the Kuiper belt, and then, God forbid, the Oort cloud and all that stuff. So don't even start thinking about interstellar missions or anything like that. It's just a no-go. Once you start Googling some of the distances and the speeds, just don't even worry about it.
Yeah, I'm already old enough that if we begin development on a ice giant orbiter, like in the next few years, it will be wrapping up its prime science mission when I retire. So I hope we start soon.
Yeah, you'll be the graybeard in the room, just sitting there watching the interns, telling them what to do.
Yeah, we'll see.
Okay, Dr. Cross, you've had some time to think about. So what I've got for your mysteries are the Enceladus plumes, and you'd like some more lunar sample return, which, of everybody in the solar system, we have several kilograms of lunar soil. So lunar scientists are absolutely spoiled when it comes to stuff. We're breaking our backs just to get a few grams from Mars, but nonetheless, you want more. So what do you want to do with the Enceladus plumes, and how are you getting stuff back from the moon?
So the plumes, this would come down when thinking about actually planning a mission. Um, the first primary driver would be, all right, how do I actually navigate the plumes to get down into the subsurface? Like I want to get into that subsurface to determine the extent to which there might be a liquid and actually be able to navigate around in there and explore. That might be challenging, and that might be expensive. So when thinking about missions, there's often in that mission planning process, there's like, all right, what would we love to do, and what are the instruments that we would need on board to to fully explore that region, and then start to come up with an initial concept, and look at some of like the the propellant needed to make that happen, the mass, the power generation. How do we do that that far out in the solar system, and then potentially within the surface of another body? And after some initial design considerations, you might realize that, oh, this is starting to get fairly expensive in order to really achieve this. Now, can we achieve a similar amount of science return by flying through the plumes? So can we develop some kind of maybe it's an orbiter, maybe it's a dedicated orbiter for that moon that is able to repeatedly fly through the plumes in order to either directly sample, or maybe it's using various types of imaging systems in order to sample the plumes. But then maybe looking at all right, what are the orbital dynamics associated with entering into an orbit around a moon, which is itself orbiting around a giant planet. So perhaps maybe we're looking at trying to do some kind of Saturn orbiter, which is then able to repeatedly go back, or periodically go back through near Enceladus, and maybe try to navigate through those plumes. Or maybe it's like a one-shot probe that we track a plume, we enter into it, send as much data back as we can, and then that's the end of it. It crashes on the surface. And so there's different modes by which that particular feature can be studied, and different mission modalities by which to explore. However, it'll come down to determining, all right, what is the trade-off between how much data can we return versus what is the complexity of making that happen. But I would want to try to fly through the plumes and repeat that at least a few times, and have some kind of, I don't know, collector. I mean, if we look at missions that went to like comets and were able to capture dust from comets and bring back, like can we employ a similar kind of technique to capture some of that plume material, and then analyze it in situ, and then send the data back. So I would want to fly through those plumes to see if there's any type of signatures for biologic activity. And then, so that's Enceladus, and then the moon. So yeah, I mean, you're certainly right. The lunar science community is quite fortunate. Like there are still lunar samples, and I think there are even some lunar samples that have not yet been opened and are remain pristine, or as pristine, as they were collected, but still untouched by scientists so far. So like there are still lunar samples to be investigated. But as I said, those are from small constrained areas, and a lot of the bulk of the material came from crewed missions to the surface that landed at relatively safe areas. So if I was interested in, say, what is the volatile content in the permanently shadowed regions? So when I refer to volatile content, I'm referring to the amounts of trapped gases that would be contained within the regolith that doesn't get burned off from heating from the sun. If I wanted to have a better understanding of how much of that volatile content is contained within those permanently shadowed regions, I'm not looking at sending a crewed mission there. I would need a robotic mission to be able to probe and analyze the surface. And even at that point, I may not even need to return those samples. I would just want to have greater instrumentation that can analyze those samples in situ, but in different regions of the moon that we don't currently have any samples from. And if I was addressing like a specific kind of question, for example, if I wanted to understand the past cryovolcanic activity, I would look on the surface for like where are examples of what we believe to be evidence for past volcanic activity. And so I might be looking at where might lava tubes exist, or where might like fluvial fans exist, or any kind of evidence for volcanic activity. And I'd want to go to the surface and sample any kind of like pyroclastic material. And again, wouldn't even necessarily need to bring it back to Earth. It would be ideal to bring it back. But being able to better sample and analyze the material in situ would answer a number of questions, or be able to contribute to the answer, because it's difficult to provide definitive answers from, again, another single mission to one region. It's all about building up building up the science and knowledge return to get a better understanding of these regions and of these features, and answering these questions. But they'll there won't be definitive answers. They'll just contribute to the answer.
All right. So we've got a potentially Enceladus, or at least Saturnian system orbiter, and maybe a series of landers to the moon, by the sounds of it, with in situ. There's all sorts of in situ chemical analysis, material analysis, the SAM instrument, one of the older ones. There's new ones, of course, that Raymond would know well, that are going to be on 2020. So I'm sure in your research, you will all find various instruments that exist for testing things robotically without us being there. We can bring tiny little laboratories with us. They're not great, but they're on another planet. So, they have to be small.
And what's neat about, particularly in recent times, is the amount of instruments that have been proposed to answer these questions, to study these samples. And so there's a ton of resources available in terms of identifying, what kind of instrument could be used to, help, constrain the age of this particular, feature on the lunar surface. What suite of instruments would be suitable for this activity, and yeah, so robotic. I'm pro robot. So yeah.
All right, Dr. Francis, you're up. You're talking about Neptune and Uranus, finding out more about them. How do we do that?
So yeah, to start with the ice giants, I think, I said we only had one flyby of each of them, and aside from remote astronomy, that's it. And I think, we had a lot of success at Jupiter with Galileo mission that lasted a long time. The next planned missions there are both long duration orbiters that will look at the moons. There's a European and a US mission in development. And similarly at Saturn, we learned a lot with the flybys of Voyager, but then we sent Cassini, and it spent about 12 years orbiting there and studying all the moons. So my first, my like dream mission for the ice giants is like a Cassini type mission that you would send with 30 years newer instrumentation to one of those. There might be a model where you could figure out with a single launch to send probes to both. I don't know if that's affordable. And there's probably a trade-off between, like, what if you could have flybys of both, or you could have a long duration orbiter of one? Which would you want better? I don't know. There's some trade-off to be processed there. But leaving aside that, long duration observations are very valuable, especially for the outer parts of the solar system, because what we saw with Cassini is that staying there for that long got us about half a Saturn year, and we got to see seasonal changes in the planet. Now, these planets, Uranus and Neptune, have very long years, and so if you want to see anything about how they change over time, you need to stay there for a long time. But even if you didn't have that hope, and I think staying there for a whole year is a lot to ask, given the length of the orbital periods. But even without that, just having lots of measurements is better. There's so many satellites, so many moons in orbit of those planets, and they're so diverse that you really want to have a lot of time. The other, so from a science perspective, I would want to look at the planet, but I would also want to look at its satellites. And if you're going to look at the satellite, you want to map as much of the surface as possible, because some of them have really diverse surfaces that don't look the same on the lead hemisphere or on the planet-facing hemisphere as on the opposite side. So, okay, that's what we want to do there. You should also, I should say, look at the environment around the planet with like magnetospheric measurements and things like that, because that will tell you a lot about the interior. But I think, I mentioned time. Another reason to dwell for a lot of time there is that the bandwidth for sending data back from the far outer reaches of the solar system is very limited. For Neptune or Uranus, you're looking at a distance that's something like 20 to 30 times the distance to Mars, and your radio power and your bit rate go with the square of the distance. So this is a much lower radio performance, which means sending data back is going to be hard. So the longer you're there, the more time you have to send back data. But of course, if you're taking pictures all day, every day, you'll never send it back. So then now we get to one of my favorite topics, which is you probably need onboard intelligence. You probably need a spacecraft that you can teach or train how to decide either which data to take, or having taken a whole lot of data, which data is really interesting to send back. Maybe you compress the data intelligently. Maybe you decimate the data. You say, look, here's the most interesting 1/10 of the data. And of course, then you need a computer that knows what interesting means in planetary science. And that's, there are some like that, but this is still kind of cutting edge. So yeah, my like dream Ice Giants mission is one that lasts a long time, looks at a lot of things, and has the smarts to be an effective tool so far away from our reach. So for the Ice Giants, I think that's how I might approach it.
And I forgot, if you want to mention quickly your Venus. You mentioned Venus. Did you have any ideas?
Yeah. I mean, it's worth saying a couple things there. I think for Venus, my favorite things there would be in situ surface geochemistry. Get me a measure. What is it made of? We have like one data point from one crummy instrument that landed there and lasted like minutes.
We also have a lens cap.
We also got a measurement of the lens cap, which like, I mean, it's laughable, but it's heartbreaking, Anyway, so in situ surface geochemistry would be nice. And while you're there, make some atmospheric measurements, because you're in the atmosphere and it's a weird atmosphere. I think there's also a niche for long duration in situ atmospheric missions. you could probably find a way to make a mission that stayed in the atmosphere, possibly, you might have a better view of the surface from there than from orbit, and you might find a way to remain aloft for a long time. And I think that would get you in situ measurements of the atmosphere, but also remote sensing of the surface, and you would get, you would get a long baseline. Venus also has some weird time questions with how slow it rotates, but how quickly the wind moves around the planet. So time is also a thing there. And I'll also just like toss in that if you wanted to look at small bodies, please consider diversity and consider the multitude of the bodies that are out there, and get both physical and chemical measurements of those small bodies.
Awesome. Yeah. And I mean, Venus, there's also the magnetosphere question, and maybe some sort of gravimetric mission there, like a Grail type thing to figure out what's the deal with the core, because there doesn't seem to be a magnetosphere, yet there's this thick atmosphere, which is not aligned with our understanding of how these things work.
Yeah, and it seems to be geologically active, so maybe
Right.
you look at the inside that way, because you can't look through the clouds very easily without certain wavelengths of radar. So yeah.
Yeah. So all good. I'm recognizing the time. Neither of you really set off the planetary protection alarm. Matt, I think you came closest. If you were talking about a probe into the Enceladus geysers, I think I would slap you on the wrist and say that better be a very clean probe, because as we'll talk about later in the course, we do want to be careful. The environments that may harbor life may be very fragile compared to what we're used to on Earth, where if you just leave a sandwich out for a while, you'll get life. Here, or in the solar system, we want to be careful. Also, we want it to be its own thing, not our thing.
It's a good reason to send robots.
Exactly. Agreed.
Yeah, so that would, thinking about a trade-off study for different approaches to say sampling the plume. You are correct that planetary protection would probably preclude going into the surface or going into the, and getting into the subsurface and into that aquatic environment. So planetary protection would probably preclude that possibility. But so flying through the plume after it's already been ejected, that would probably be acceptable and pass that kind of review process.
Or you could propose a way to try and meet stringent planetary protection requirements with an in situ measurement, but I would be interested to see that approach.
You did get bonus, for the lunar landers, especially if you're going to cratered or shadowed craters, the landers are much safer. Humans, whilst they can be safe while they're there, humans do things like poo and whatnot, and that needs to go somewhere. And there's only so much distance we can cover on the lunar surface. And are we leaving it there, or are we bringing it with us? And if we're even near any volatiles, how far away do we want stuff like astronaut poop? So your lander's got some points there, because bringing human poop to the South Pole is concerning, for me at least.
Now, didn't they leave some samples on the surface, and isn't one of the proposed missions to go retrieve it, just to see what has survived?
I don't know, maybe.
Yeah. That's one approach. I'll mention that spacecraft also have their effluents, and so you should be thoughtful, for example, if you're landing a robotic mission, of where you landed. If you go down with rockets, and you might fill rocket fuel is highly volatile, and you might fill your landing area with volatiles. You probably don't want to sample those ones. So that one might put some thought about how to get around that problem.
So, I mean, we could probably talk about this all night. There's endless considerations for landing robots on planets and moons. Don't kick up a bunch of dust when you land, because it might just bury your rover or other things like that. How do you get a rover to the ground without having the landing probe too close to it, or some sort of crazy sky crane? There's there's all sorts of things you can do. So I hope you definitely have gotten an insight into this. I'm curious, the lighting is really bad, but the picture above Captain America, can either of you make that out?
Is that a Viking image of
No,
Mars? No, what is it?
no, because it was rolled up at once upon a time. The light really reflects off of that.
Hmm.
It is a miniature version of the painting in Picard's Ready Room.
Oh.
Prize. Yeah.
Oh, okay. Now I see. What I thought
Yeah.
was like the crescent of a planet is actually a starship, and its surroundings.
Yeah. Yeah.
I see.
Yeah. Yeah. Not very good lighting in here. Okay, yeah, so we've covered pretty much everything. I don't think I had anything else to ask. Is there anything you guys want to offer?
I think I covered most of what I wanted to get in there. Yeah. I mean, we didn't talk about Mars at all. That's a cool place, but I think maybe it's helpful. You know, your students will see that there are many Mars missions actively, so there must be a reason to go there.
Yeah.
But I think we've done a good job of giving reasons to go to the rest of the solar system.
Yeah, the students will hear your voice recorded a year ago discussing Mars 2020, which I'll have to create a new preface for. That it is on its way to Mars now. Dr. Cross, anything on your end?
Only just to recap that the solar system is interesting. There's a lot to it. I mean, there are a lot of current active missions, either on their way to Mars or presently at Mars and proposed for the moon, and those do get the most attention. But the solar system is very diverse, and they're, particularly for an assignment such as this, just from the interest perspective, it might be interesting to pick something that there isn't a lot of information about. Just to really think about, how would we study this? What are those questions that are unanswered? Because there is some planetary scientist somewhere who has written a LPSC abstract on some planetary body or some planetary object, and they are keenly interested in that for some reason. And I can't imagine that there are many bodies in the solar system that don't have something. Like, there's going to be someone who's interested in everything. And so, don't constrain yourselves to the moon or Mars just because they're there and they're easy and it's done. Try to have a little fun with, finding out what's really interesting in the solar system.
Yeah, and I made a similar comment early on. Like, the solar system is huge. There's lots of interesting places to go, and just because we picked 4 or 5 of them between the two of us to highlight, like, there are lots of other things to do. So, I would encourage them to explore and find interesting places. I don't think it's a win for the assignment. They should not have the impression that they will get extra marks for picking the same thing that I did.
No. Yeah, that's a good point. But yeah, you both bring up something that I've geez, it already escaped me. But oh yeah. No, I mentioned earlier, pretty much whatever body, I guarantee whatever body you pick, there is a planetary scientist out there who may have dedicated a better part of their life to understanding even just a region of it. And the more popular the body, the more specific you would probably get. So yeah, don't fret. There's lots of places to go. Raymond?
Yeah. Oh yeah. You might even find, for example, you pick, like, one of my very first experiences at the planetary conference at LPSC was sitting in a session where they were providing descriptions of the interior of Ganymede. This is a big moon. We know a lot about it.
The biggest.
Most bodies in the solar system. And somebody went up and presented, look, here is a model for the interior of Ganymede. It's got these layers this thick and this structure and this composition, and it fits all the data, and I can be very confident. And then the next presenter got up and said, here is a model for the interior of Ganymede. It fits all the data, and the two were completely at odds. They didn't agree at all, right? but they both fit all the data. So there's a lot to do yet.
They're mortal enemies, those two. I bet they
I suspect that they get along very well, because what they both want is more data.
Yeah, that's true.
On Ganymede.
All right. Well, thanks to both of you. You've fulfilled your Western alumni requirements this year. Raymond, you continue being an adjunct professor.
That's right. Yeah, and I've done my duty for a little while.
Matt, this is your service as part of your postdoc contract.
Excellent.
You're all good. Yep. So yeah, thanks so much. I'll wrap up the recording. We'll say goodbye to each other without the students watching. But yeah, I hope you all enjoyed this.